Where's everybody? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's supposed to be. Supposed to be 17. Okay, I guess we better do something. Let's look at our schedule real quick. So this is the 27th. We started, got most of the way through chapter 1 last time, which was 2 weeks ago. So we got to finish that chapter, and then you're going to be so glad you came tonight because we get to do chemistry, which I've been hearing all kinds of happy comments about that. But it won't be so bad. Don't freak out. So you guys all did the introductory quiz. Thank you. That was good. But the first the chapter 1 quiz and short answer questions are due tonight, right? Tonight at midnight. Everybody going to be able to get that done? Okay. If you have if that's a hardship for you for any reason, let me know. I can reopen it for a day or two. Just let me know. Okay, anything else we need to talk about before we get back into chapter 1? So on the schedule it says anatomical terminology lab. Gave a handout last time, and so we can look at that, go over that, and make sure you got those answers okay. And okay, I think I have extras. Anybody else not get the handout, or you didn't bring it with you? You need one? Need a copy? Jen, let's see. Yeah, here, yeah, it's that one. You got the right one. I think I got only one copy left for myself. So if you need a copy, let me know. I'll go I can make some at break time. And since we're going to be getting partway through chapter 2, I got the little bit of chemistry experiments we can play with also. Okay, I need you guys to help me because I have no idea where we left off. I don't remember how far we got in chapter 1. Directional, okay. Let's do this. Yeah, so we went over this list, right? Is that where we stopped? Around there somewhere? Oh yeah, this stuff, right? Yeah. The sections or planes. So different ways that the these imaginary cuts can be made through a human body so that we can see inside. And many of the diagrams and photographs in our textbook and PowerPoint are this kind of views. So these terms, sagittal, frontal, transverse, they indicate the orientation of the cut. So a transverse plane is a horizontal cut, and it can be at any level in the body. So if we, any way we would cut this guy in this direction, it would be a transverse section. Sagittal would be this way, cutting into left and right parts. If it's right down the center line, then we call that mid-sagittal. Sagittal section right in the middle. If it's off to the side, we call it parasagittal. And then the frontal would be cutting in this way into a front and back parts. And so which kind of cut is taken just depends on what we're trying to visualize inside. So here's those definitions. So here's an example using a human brain. It's cut this way, and then this way, and then this way. Okay, body cavities. A cavity is it's a space in the human body. It's hollow, but it shouldn't say it's hollow because it can have organs in it. For example, the cranial cavity. The cranial cavity is what is surrounded by the skull. That's where the brain is located. And in fact, this part of the skull that surrounds the brain is called the cranium. The spinal or vertebral cavity it's like a tunnel down through the whole spinal column. So the spinal column or vertebral column is all these backbones just stacked on top of each other, and there's a hole, a vertical hole through each one of them, and those holes form a continuous tunnel all the way through that spinal cord, and that's spinal column, and that's where the spinal cord is. The word thoracic means chest, or thorax means chest. So the thoracic cavity is where the heart and the left and right lungs are located. And let's find a picture. Okay, so here's a diagram showing, so this would all be the thoracic cavity. The heart in the center and the right and left lung. And this word mediastinum just means the location of the heart in the center of the chest, right behind the breastbone or sternum here. The heart is surrounded by a double membrane, so two layers of membrane called pericardium. So that's shown here. Pericardium. So there's two of them. The visceral one is the membrane that's right on top of the heart. It's called the visceral pericardium. And then to the outside of that is the parietal pericardium. And in between those two membranes is called the pericardial cavity. So the pericardial cavity is not in here where the heart is. It's in between the these two membranes. And that pericardial cavity has a thin layer of slimy, lubricating liquid called serous fluid. Is that on here? Yeah, well, that word serous fluid. So the pericardium membranes are called serous membranes, and the fluid in between them is called serous fluid. Yeah, there it is, serous fluid. So similarly, each lung is surrounded by a double membrane called pleura. And again, the inner one is called the visceral pleura. The outer one is called the parietal pleura. And in between is the pleural cavity, where there's a thin layer of that serous fluid. And so that's fluid, that's lubricating fluid in between there. It just allows, when your lungs inflate, it allows the lungs to move move independently of the surrounding organs because of that lubricating fluid. Same thing when your heart beats. It can fill up with blood, and then it can contract, and so it gets big and then small and big and then small, and that layer of lubricating fluid in between those membranes allows it to do that independently of the surrounding organs. The abdominopelvic cavity is down here. The upper part is sometimes called the abdominal cavity, and then this lower part surrounded by the pelvis or the hip bones is called the pelvic cavity, but it's really one big space that we can call the abdominopelvic cavity. And that's where the stomach and pancreas and spleen and small intestine and large intestines, they're all located within that abdominopelvic cavity. And it is surrounded by two membranes. Oops, sorry. Well, it's called the peritoneum, where it's not shown in any of these pictures. Peritoneum. Well, there's a double membrane surrounding all of this called the peritoneum. The peritoneum. So again, the inner one is called the visceral peritoneum. The outer one is called the parietal peritoneum. The word viscera just means internal organs. So the inner one is called the visceral peritoneum because that's the one that's right up against the organs, the heart or lungs or the abdominal organs. What's labeled here, the diaphragm. This is a broad muscle that goes all the way across below the heart and lungs and above the liver. But so it divides the thoracic cavity from the abdominopelvic cavity. And it's also, what does that muscle do, the diaphragm? When do we use that? Do you ever use that muscle? Think you're using it right now? It's a breathing muscle, right? It's in this arched position, so it's kind of like this when it's relaxed, but when you inhale, that muscle is contracting and it moves down and it enlarges your lungs so that air comes in. And then when you relax that muscle, your abdominal organs push it back up and force the air out of your lungs. We also use some muscles um, some rib muscles for breathing. We'll talk about that. Well, that's in anatomy too, right? Okay, that's all we need to know about um, cavities, body cavities. Um, so here's a transverse section at the level of the heart and lungs. So here's the heart, here's the breastbone or sternum here. Um, the left lung, right lung. These are blood vessels. Um, this this section cuts through these blood vessels at an angle. That's why they look like they do. This is one of the valves of the heart. Um, what's this yellow stuff?
Man.
It's fat. It's just a subcutaneous fat. It's just a layer of fat that we all have right below the skin. And there's some more of it just in between, fills up space in between organs. And then what's this stuff? Looks like meat. It's muscle. Yeah, that's what meat is, muscle, right? Here's one of the backbones, one of the vertebrae. And there's that tunnel, that hole through it. So that's the spinal cord in there. Okay, and these abdominal pelvic regions and quadrants. So there's two ways that we can divide up the abdominal pelvic area. One is into these 9 regions. Each one has a name. The other way, the simpler, is quadrants. The word quadrant just means 1/4 of something. So simply right upper, right lower, and right and left lower. That's pretty easy. Um, these are what are used. These quadrants are used in medicine. I don't know of these regions being used in medicine very much. Um, if you're describing the location of pain and tenderness in the patient's abdominal pelvic area, you would probably use quadrants. You'd say the pain and tenderness in the right lower quadrant or something. What would that probably be? Appendix? Yeah, that's where the appendix is, in the right lower quadrant. So, but these regions, we need to learn these. So right in the center, the umbilical region, that's where the umbilical cord was attached. The belly button is right in the center of that umbilical region. And the others are to the left and right and above and below that one. So right above that, epigastric. Epi means above, so and gastric means what? What's the word gastric? The stomach, right? So above the stomach, so here's the stomach right here. So it's kind of most of it is, I guess, above the stomach. Below that, hypogastric. Hypo means below, so it's way below the stomach. And to the left and right are the lumbar, left and right lumbar regions. Down here to the left and right of the hypogastric are the iliac, left and right iliac. The when we study the skeleton, we'll learn that this part of the hip bones here, that on me you can feel it because I'm pretty skinny, but it's called the iliac crest, and these are called the iliac bones. The Each hip bone is actually made up of 3 bones fused together. It looks like one big bone, um, but this part is called the iliac. Uh, and then above here, hypochondriac, left and right hypochondriac. Um, that word hypochondriac has a different meaning, doesn't it? What does it mean to be if someone is a hypochondriac? Are any of you think you're a hypochondriac? No. A hypochondriac is someone who always thinks he's sick. Or, like if if a hypochondriac took a class like this, then every time I'd mention a disease or something, he'd say, "I think I have that. I think I have those symptoms." Um, but I don't know why they use the same word for something that seemed to have nothing to do with that psychological disorder that we call hypochondriac. Um, okay, yeah, this medical imaging, don't worry about this. You don't need to learn this. Um, I just leave it on here because might be of interest to some of you, but it won't be on exams. So any questions about this chapter 1 stuff? I guess I'll go ahead and start chapter 2 now, and then we'll do lab stuff later. Uh, a little from both chapters. So, I'm trying to record this class. So I have to I hope it's working. We'll see. Okay, chapter 2. Chemistry. Well, how many of you have had a chemistry course in high school or college? I know you did. Anybody else? Okay. I have to take pretty much chemistry to be a biologist, and I suffered through it, and I don't like chemistry any more than you guys do. I never felt like I was a very good chemist, and I could learn the stuff, but I never really understood it. A lot of it, I don't really get it. Um, but I think I've had students tell me that I'm good at teaching chemistry. Um, And I think if that's true, it's because I had so much trouble with it. So when I'm explaining it, it's like I'm trying to explain it to someone who is as dumb as I was when I was trying to learn it. So try to explain it simply. Um, okay. Um, so what is chemistry? Study the composition of matter and how matter interacts and changes. So we'll define what matter is in a minute, but so knowledge of chemistry necessary for understanding of physiology. Much of physiology is chemical reactions going on inside of our bodies, so we can't really understand physiology without having at least a basic knowledge of chemistry, and I'm trying to limit what we cover in here to only the concepts that are important for us to understand physiology. Um, I don't want to make this any harder than it has to be. Okay, what is matter? Anything that has mass and takes up space. So matter is just physical stuff. So an example of something that is not matter is energy. But energy does not have mass. It doesn't take up space. Um, The word mass. Mass means kind of the same thing as weight. It's just a measure of the amount of matter. Um, but the difference between mass and weight is that weight is actually a force of gravity acting on a certain amount of mass. So if we say something weighs a pound, what we mean is that um, gravity um, is that it's the amount of mass that the Earth's gravity um, is pulling on with a force of 1 pound. Um, if but the mass is actually an amount of matter, but weight is actually a measure of the force of gravity acting on that amount of matter. So the mass of something, like the mass of this, would be measured in grams or kilograms, and that would be the same anywhere in the universe. But if we would go up to the moon with this, where the force of gravity is about 1/6 of what it is on Earth, the weight would be different. It would be less. Um, Okay, matter exists in solid, liquid, and gas. And we'll talk about the importance of that a little bit later, especially regarding water. Okay, so all matter is made up of atoms. Atoms are just tiny bits of matter, and matter is made up of elements. Elements are just different kinds of matter, and the what makes one element different from another is the types of atoms that make up that element. So elements, some examples of elements here, you're familiar with all of these: oxygen, carbon, hydrogen, nitrogen. Um, there's there's over 100 different elements that make up all matter, but an atom of the element oxygen is different from an atom of the element carbon, which is different from hydrogen, and so on. And what's different about the atoms is the size of the atoms. Um, uh, Atom of hydrogen is real small. An atom of oxygen is larger. And atoms are made up of three smaller particles: protons, neutrons, and electrons. So I'm sorry, I'm skipping around a little bit. Protons, neutrons, and electrons. So let's look at a diagram of an atom. So here's two different diagrams of an atom. They look different, but they're showing the same thing, just in slightly different ways. So three particles. We call these subatomic particles: the protons, neutrons, and electrons. The protons and neutrons are in a cluster here in the center called the nucleus. And when we study cells, we'll see that a cell also has something we call a nucleus. It's the same word, but a very different meaning, so don't be confused by the nucleus of an atom versus the nucleus of a cell. They're different. But the electrons are out here, and they're shown in these circles. And they're drawn like that because they move around, they spin around the nucleus in these circles, like the planets orbiting the sun. And they don't stay exactly this distance out from the nucleus exactly in these circles. It can move closer and farther and closer and farther. But this is the average distance of these two electrons from the nucleus as they spin around. These four out here, again, this is the average distance, but they can move closer and farther. So that's why this other diagram is shown as an electron cloud, because those electrons can actually be anywhere in this cloud. But this just shows these orbits in which they are spinning around the nucleus. These are called electron orbits or electron shells or energy shells or electron shells. I said that twice. Uh, those terms all mean the same thing. It's just these orbits with the electrons spinning around the nucleus. The size of or mass of a proton and an electron are about the same, but the mass of an proton and neutron are about the same, but the mass of an electron is much smaller. It's about 1/2000th the size of a proton or a neutron. Important difference among these three subatomic particles is their electric charge. They have a static electric charge on them, which means static means not moving. So it's not like electricity flowing through a wire. It's just an electrical charge that's stuck on that electron or stuck on that proton. And on a proton, it has a positive static electric charge. On an electron, it's negative. But a neutron has no electrical charge. We say it's electrically neutral. That's why it's called a neutron. So the size of the electric charge on the proton is the same size as on an electron. They're just opposite. One's positive and one's negative. So what do we know about opposite electric charges? How do they affect each other? Opposites attract, right? Opposites attract. You've heard that. So these electrons are spinning around here really fast. We say they have a lot of energy. They're spinning around the nucleus. If the electrons are negative and the protons in here, that's red, right? I'm colorblind. If these are positive and these are negative, they're attracted to each other, right? So why aren't the electrons pulled into the nucleus? Same reason that the planets orbiting around the sun are not pulled into the sun by gravity. There's gravity in between the sun and the planets. But the planets are moving so fast in their orbits that centrifugal force balances the gravitational attraction from the sun. So they stay out there in their orbits. And so same thing here. These are spinning around here so fast that they don't get pulled in to the nucleus. So opposites attract, but the same charge or like charges, they repel each other, right? So two particles that are both positive would push each other away. So why don't these protons, they're all positive, but they're together in a cluster, why aren't they flying apart from each other? No, it's not because of neutrons. It's I shouldn't ask that question. I just thought you might wonder about it.
It's some type of bond, ain't it?
It's some kind of bond, but
It ain't covalent.
it's not. No, it's that's a very complex question. I'm not smart enough to understand. I know the answer, but I'm not smart enough to understand it. Albert Einstein was smart enough to understand it. That's called nuclear physics, the physics of what goes on in the nucleus of an atom. And before Albert Einstein, nobody knew what's holding them in there. Why don't they fly out? It just doesn't make sense. And he figured out that there's a mysterious force in there, in the nucleus of an atom, holding those protons together. there's a tremendous amount of energy in that nucleus of an atom. You've all heard of this, E equals mc squared. Most people have heard about that. That's what that's about. The energy. If you would take these each of these protons out and measure their mass, and then you would measure the mass of the nucleus, you'd find that there's some mass missing. The mass of those protons and neutrons added up together is a little bit more than the mass of them all together. It's like impossible. How could that be? It's like if we weighed 10 people individually and then added those weights together, and then we put all those 10 people on the scale at one time. It wouldn't. There'd be some weight missing. What happened to it? Some of that mass is converted into energy, and that's the energy that's holding this together. And this c squared is the speed of light, huge number. So the amount of energy in there is equal to time, is equal to that missing mass times the speed of light squared. That's a gigantic number. So that's even though it's a tiny bit of mass that has been converted into energy, it's converted into a tremendous amount of energy. That's why if you split the nucleus of an atom, a lot of energy is released. That's how an atomic bomb works, or a nuclear power plant. That's how you get so much energy out of a small amount of radioactive material in a nuclear power plant, because of that mysterious force in there holding those protons together. And you've heard of radioactive isotopes like uranium. They're dangerous because that means that these protons aren't held together all the time. So once in a while, one will come flying out, and that's what radioactivity is. The nucleus of the atom is flying apart, and those high energy particles are what cause radiation sickness and stuff. Anyway, that's we don't need to. I just think that's interesting, even though I don't understand it. But, okay, back to the more boring stuff. Okay, so there are only 2 electrons in this first shell here, but and then this shell has 4, and it's not random that they're like this. They will learn how these electrons are always arranged, like 2 in the first shell, so many in the second shell, and so many in the third shell, and why that's important. This periodic table of the elements, that's what this is. There's a poster of it here. Most chemistry and biology labs have one of them on the wall somewhere. So this is just a big chart that lists all of the 100-something elements. And they are listed from the smallest atoms, going across each row. The rows are called periods, that's why it's called the periodic table. They just get bigger. The atoms get bigger across each row. And so these are, this is the smallest atom, hydrogen. It's just 1 proton and 1 electron. Not even any neutrons. This one's helium has 2 protons and 2 neutrons. Normally the number of electrons is the same as the number of protons, like seen here. There would be 8 protons here, and 6. This one has 6 electrons. The number of protons would also be 6. The number of neutrons is not necessarily the same as protons or electrons. Um, um, so this first electron shell can only hold 2 electrons ever. But this atom has 6 electrons, and so the other 4 go in this second electron shell, and that second electron shell can hold 8 electrons. You need to remember that. So first shell 2, second shell 8. Let's look at some other. Here's another bigger atom, has more electrons. So here's the first shell, has only 2. The second shell has 8. That's all it can hold. But it has 1 additional electron, so it's in a third electron shell. That third electron shell can hold 8. That's called the octet rule. Oct means 8 of something, like an octopus has 8 tentacles. An octagon is an 8-sided figure. The octet rule: 2 in the first shell, 8 in the second, 8 in the third, and beyond that, if there's a fourth shell, it gets more complicated than just a number 8. But because because we're in a human anatomy and physiology class, we don't care about big atoms with a lot of electrons, because there's about 24 or 25 elements that are normally, naturally in your body. They make up your whole body, and all of them are up here in the top part of this periodic table. So the biggest one is iodine here. We have iodine in our thyroid gland hormones. So we normally have iodine in our body, but I think all of the other ones are just in these first 4 rows. None of these. We don't in biology, we don't care about any of these down here. I don't care about them. Unless you were a biologist who was studying toxicology, toxins or something, because down here, here's mercury and lead. There's lead down here. These so-called heavy metals that are toxins, and we all have some lead and mercury in our bodies, but it's not supposed to be there. They're toxins. But we do have lots of hydrogen and carbon and nitrogen, oxygen, sulfur, phosphorus, sodium, magnesium, potassium, calcium, iron, copper, zinc, so on. But so that octet rule, all we need to remember is 2 in the first shell, 8 in the second, 8 in the third. Beyond that, the number of electrons gets so big that we don't care about them, because those big electrons, those big atoms that don't occur in the human body anyway. We don't care about them in anatomy and physiology. Okay, so sorry I'm skipping around so much. Okay, these terms, atomic number and mass number. The atomic number is just the number of protons in an atom of a particular element. So in hydrogen, the atomic number is 1, because an atom of hydrogen has just 1 proton. So that's what determines what element an atom is. How many protons in the atom, which we call the atomic number. If an atom has any number of protons other than 1, then it's not hydrogen, it's something else. The mass number is the number of protons plus the number of neutrons added together. So we saw that in hydrogen, there's just 1 proton and no neutrons, just one proton and one electron. So the mass number is the same as the atomic number in hydrogen. But in this, which is carbon, the atomic number is 6, has 6 protons, but the mass number is 6 plus 6, 6 protons plus 6 neutrons. So if I would tell you on an exam, if I would tell you, if I would give you the atomic number and the mass number of an element, and I would ask you how many protons and how many neutrons and how many electrons is in an atom of that element, you should be able to figure that out pretty easily. So if I would say, tell you the atomic number is, I'm just making this up, 27, and the mass number is 52, then what's the number of protons, the number of electrons, and the number of neutrons in an atom of that element? So this one should be easy. What's the number of protons? 27, because that's what the atomic number means, the number of protons. So that's easy. Sorry, this marker's not very good. So the number of electrons, I said normally, in a normal atom, the number of electrons is the same as the number of protons. So that should also be 27, right? So how would we get the number of neutrons? So this is a number of protons. This is a number of protons plus neutrons. So to get the number of neutrons, we just subtract the little number from the big number, right? And so what is that? 25? Right, so that should be pretty easy. So the number of positive protons is the same as the number of negative electrons, and therefore we say that overall the atom has no electrical charge. It's like it's got the same amount of positive and negative stuff. So overall, or we say the net electrical charge is 0. The whole atom is electrically neutral. There's another example, practice questions. This concept called the atomic mass or atomic weight. I don't want you to worry about this, but explain briefly what that means. We'll look at this periodic table again. So these numbers in the upper left corner, that's the atomic number. So hydrogen has 1 proton, helium has 2, and this one, lithium, has 3, then 4, 5, 6, and so on. And this number down below here, that's that atomic mass or atomic weight. And that number is very similar to the mass number. It's very close to the mass number, but it's just a tiny bit different. And the reason for that is isotopes. An isotope is atoms of the same element that have a different number of neutrons. We said the number of protons is always the same within an element, but the number of protons can be different. An example of carbon, most carbon atoms, like 99% of carbon atoms have 6 protons and 6 neutrons, so we call that carbon-12. That's its mass number. But there's a tiny number of carbon atoms out in the universe that have 8 neutrons. And there's some that have 7 neutrons. And so we call them carbon 14, carbon 13. They have a different mass number. So this number here, it's carbon. We said that almost all carbon atoms have mass number of 12, but this number 12.011, that's just a tiny bit higher than 12, because this atomic mass, that's supposed to be the average mass number of all the carbon atoms in the universe. So almost all of them are 12, but the tiny number of them are 13 and 14. So if we would average them all together, then the average would come out to be just a little bit above 12. So that's what that atomic atomic mass or atomic weight is about. But don't worry about that. It's not gonna be on an exam. So why are these elements arranged in this weird way on this periodic table? All of the elements in each row or period have the same number of electron shells. So this hydrogen has only one proton and one electron. That electron's in its only electron shell. Helium has 2 electrons, still just 1 electron shell, but this one has 3 electrons, so it has 2 electron shells. This one has 4, 5, 6, 7, 8, 9, 10 electrons, so 2 in the first shell, 8 in the second shell. Now, for this one has more electrons. This row has 3 electron shells. And these all have 4 electron shells, and so on. And in any column, vertical column, these elements have the same number of electrons in the outermost shell. So this one has only 1 shell with 1 electron. This one has 2 shells, 2 in the first, 1 in the second. This one has 3 shells, 2 in the first, 8 in the second, and only 1 in the third shell. This will have 1 in the fourth shell, 1 in the fifth shell, and so on. These over here, all of these have their outermost electron shell full of electrons. And that makes these special, that they have their outermost shell full of electrons. Why is that special? Because come back, I'm skipping around again. Well, atoms that have their outermost electron shell full are, we say that they're stable. An atom that's stable means that it's happy the way it is. We say it's unreactive, inert. Inert just means inactive. That if an atom is stable, that means if we mix those atoms with any other kind of atoms, there will not be a chemical reaction. Remember, a chemical reaction is just a change in which atoms come together to make molecules, or else molecules break apart. But if you mix stable atoms with other stable atoms, or even with reactive unstable atoms, there will not be a chemical reaction because they're happy just like they are. And so where's the, sorry, got a picture of a stable. These are all unstable, I guess. So hydrogen has only one atom or electron in this one shell. that shell can hold 2, so it's not stable. This one, carbon, this second shell can hold how many? 8. It's only got 4. Not stable. Nitrogen, not stable. Oxygen, this is 6. It can hold 8. That's not stable. Only 1 in that shell, not stable. Chlorine, 7. It can hold 8. These are all unstable. But an example of a stable atom is helium. So helium is just one proton, 1 neutron, and 2 electrons. So that's stable because there's 1 electron shell and it's full. Can't hold any more than that. So this is stable, and look back at the periodic table, and it's in that right-hand column. All of these have their outermost shell full, and so these are called the inert gases, or it's sometimes called the noble gases. And so if you mix helium with anything else, there will never be a chemical reaction. So there's no such thing as a molecule with helium in it. Helium atoms are always by themselves. There's no such thing as helium dioxide or anything like that, because they're happy and stable like they are. There won't be a chemical reaction to make molecules with any of these in this right-hand column. All these others are unstable, and so if you mix them with other unstable atoms, there could be a chemical reaction. And so why do atoms come together to form molecules? Why would they want to do that? Atoms like to be stable, and if atoms form molecules, that's a way that they can become stable. And how does that work? Well, for example, oh shoot, this is what I was looking for. Here's a picture of helium that I drew. Helium is stable, hydrogen unstable, lithium unstable. An example of how this can be important. You guys ever heard of the Hindenburg disaster? You know what that was? The Hindenburg is the name of a big airship. This was over 100 years ago. One of the big gas-filled lighter than air, like the Goodyear blimp type thing, and that they used to fill them with hydrogen gas. Now what do they use? They use helium. These are both very tiny atoms, so hydrogen gas and helium gas are lighter than air. That's why they float. And so this is the same thing that's in the party balloons you buy at Dollar Tree. Now they fill those whole big airships with that stuff. But originally they used hydrogen, but hydrogen is unstable, it's reactive. And hydrogen is actually very flammable. You could use hydrogen as fuel for your car. It would actually be a very good fuel because if you burn hydrogen, what would come out the tailpipe? Burning something is just a chemical reaction with oxygen. So if you combine hydrogen and oxygen, water, you just have water vapor coming out the tailpipe, no pollution. But it's not a good thing to fill airships with, because there was a spark and that whole thing caught fire, and 27 people, I think, died on that airship from that. So that was a hard lesson to learn. Don't use hydrogen. Use something inert, stable, that can't burn, like helium. So this hydrogen is unstable. when it's by itself. But we got diagrams. Okay, here. If two hydrogen atoms would come together side by side, each one has one electron, but would like to have two and be stable. But if they would share their two electrons, so that both electrons would spin around both nuclei, spin around this nucleus and this nucleus, kind of like a figure eight. Then it would be as if each hydrogen atom has two electrons, right? Because they're sharing them. Now, both of those hydrogens are stable. That's what they like to be. And just like people, married people are always happier than single people, right? Atoms are happier married than single. This is why two hydrogen atoms would come together to form a molecule, so that they're both stable. In fact, there's a lot of hydrogen in the air, in the atmosphere, and that hydrogen is almost all like H2. They're not just H. A molecule is written like, you're familiar with like H2O. This is terrible. H2O means a molecule of water with two hydrogens atoms and one oxygen atom all stuck together, right? So H2 would just be a molecule, two hydrogen atoms stuck together. We call this a diatomic molecule. Diatomic just means two atoms. Oxygen does the same thing. That bottled oxygen that's used in hospitals for patients who need supplemental oxygen, on that tank, that'll be a good one here. Those tanks don't have that on it. They have O2, right? Why is that? Because oxygen atoms are happier when they're stuck together, sharing electrons, so that they're stable. So each oxygen has 6 electrons in its outermost shell. We'd like to have 8. So two oxygen atoms come together, and they share 2 pairs of electrons, two electrons from each. And that's called a double covalent bond. Sorry, I haven't defined the word covalent yet, but that's a double bond. There's two pairs of electrons. Carbon dioxide, same thing. Carbon atom with two oxygen atoms bonded to it. So that's one way that atoms can become stable, by forming molecules, and that's called a covalent bond. Co means together. The word valent just refers to the electrons in the outer shell. So two atoms come together, they share their valence electrons, and that sharing of electrons holds them together. We call that a covalent bond. Another type of bond that holds atoms together in molecules is called an ionic bond. So sorry, I've been jumping around so much, but need to define an ion. Said that in a normal atom, the number of electrons is the same as the number of protons, but that can change. Atoms can lose one or more electrons or gain one or more electrons, and then we call that an atom like that, we call it an ion. It's an atom or a molecule that has an electrical charge, because now the number of positive protons and the number of negative electrons is not the same anymore. So if an atom um, gains one more electron, now it has more negative electrons and positive protons. So the whole atom has a negative, we say a net negative charge. And so that would be a negative ion, and the term for that is anion. It's a negative ion. And we use a symbol for the element with a minus sign. So chlorine, Cl minus, fluoride ion would be F minus. This would be a molecule. That's an ion. And so this 2 minus would mean that it has gained 2 electrons. Cation is an atom that has lost electrons, and so now it has a positive electric charge, like sodium, Na plus, potassium, K plus. This one, calcium, has lost 2 electrons. Well, don't worry about this free radical. You don't need to know that. Okay. These symbols, didn't really talk about these symbols so much. Every element has a symbol. It's either 1 or 2, or in a few cases there's 3 letters. Like these one have 3 letters. And in many cases it's just the first letter or 2 of the word. So hydrogen is H, helium is He. But some of these don't make sense, like iron is Fe, potassium is K, sodium is Na. Those letters aren't in those words. Where'd that come from? This Fe is from the Latin word for iron, which is ferra, Ferra. So, in fact, metals that have iron in them are called ferric metals, like steel has iron in it, so it's a ferric metal. Potassium, K, is from the Latin word for potassium, which is something like kalim. In fact, there is a condition, a medical condition called hypokalemia and hyperkalemia. What do you think that would be? What do you think would be wrong with somebody who has hypokalemia? Not enough. Hypo means low, right? So not enough potassium. That happens to people sometimes when they're working hard outside on a hot day. They sweating out all their electrolytes, losing potassium and not replacing them. It looks like heat stroke, but it's just hypokalemia. Hyperkalemia would be too much. Sodium Na, again from the Latin word for sodium, which is something like natreme. In fact, there's a condition called hyponatremia and hypernatremia. Again, too much or too little of those ions in the body fluids. Okay, what else we need to talk about? Oh, yeah, ionic bond. So we defined ions. So what's an ionic bond? Yes. So a covalent bond is 2 atoms sharing electrons that holds the 2 atoms together. Ionic bond is just 2 ions, one positive and one negative, that's stuck together because opposites attract, right? So here's an example of what can happen. Here's a sodium atom, and this is the one that has just 1 electron out there in its 3rd shell all by itself. So this is not stable. It would like to be stable. It could be stable if it would just lose that 1 electron. Then the 2nd shell would be the outermost shell, and it's full. So now it would be stable and happy. This chlorine atom has 7 in its outer shell. It would love to have just 1 more electron, then its third shell would be full. So when those two come close to each other, guess what happens? The sodium would gladly gives up its electron, it jumps onto the chlorine, and now they're both stable and they're happy. But now they're both ions, right? Because this has lost an electron, so now it's a positive ion. So it should be Na plus here. The chlorine has gained an electron, so now it's a negative ion, and they're oppositely charged ions, so they attract each other and stick together and form an ionic bond, form a molecule, and live happily ever after together. So that forms sodium chloride, NaCl. What is that stuff? Anybody know?
Salt.
Salt. It's just what we call table salt, the kind of salt we put on food. Sodium chloride. So that sodium chloride is held together by ionic bonds. That NaCl, that implies that it's just one sodium and one chlorine atom stuck together, but many of these ionic bond molecules, they're not just one of each. It's more like this. So the chlorine, sodium, chlorine, and so they alternate in all three directions. So they're arranged in this regular three-dimensional pattern that we call a crystal. And this is why if you look at a grain of salt with a magnifying glass, it looks like a little box, right? It's because that's a crystal. The chlorine and sodium atoms or ions that are arranged in this three-dimensional crystal structure. Ionic bonds come apart in water. So if you put salts in water, when it dissolves, the sodium and the chlorine separate from each other. Covalent bonds don't do that. They don't come apart in water. In fact, water molecules themselves are held together by covalent bonds. So those are the two main kinds of bonds that hold atoms together in molecules: ionic bonds and covalent bonds. And in both cases, they happen because atoms they're doing that to get their outermost shell full of electrons. So when an atom is stable, that means it's not reactive. It's happy like it is. It doesn't. It's in a condition where it doesn't need to have a chemical reaction to get its outermost shell full because it's already full. But if that's true, then how could hydrogen burn? If we take some H2 and mix it with O2, and I said that would cause a chemical reaction. Burning is just a chemical reaction of a fuel, something flammable, with oxygen. So if these are both stable, then how could there be a chemical reaction? Well, they are stable, but if we just mix hydrogen and oxygen together, is it going to burst into flames by itself? No, because they're both stable. What does it take to cause that to happen? We need to add fire, right? Or a spark. We have to add some energy to it. Like we have to heat up some of the H2 molecules and some of the O2 molecules so that they'll separate. So that's all it takes, just a spark to get just a few of these H2 molecules to separate and a few of these O2 molecules to separate. Now they're unstable, and there will be a chemical reaction of burning, and that burning is producing heat. enough heat to make more H2 and O2 come apart and become unstable. So that heat that's produced by this chemical reaction will keep itself going. Will keep making these stable molecules unstable so they can react with each other. Okay. What else? Okay, need to talk about polar and polar and nonpolar covalent bonds. So in a covalent bond, two atoms sharing electrons. The electrons are spinning around both of the atoms. These electrons spinning around both hydrogens, those electrons would spin around both hydrogens about the same. They're not going to spend more time spinning around this one than this one because they're both the same. Same here. These oxygens are both the same. They're sharing electrons. These electrons will spin around this one and then this one, this one, this one. They're not going to spend more time spinning around this one than this one. There's no reason for that. And so that's we call them nonpolar covalent bonds. The word polar means that something is different at two ends or something. Like the Earth has north and south pole. A magnet is different at the two ends. Like if you have two magnets, you put them together one way, they attract each other. You turn one around, now they push each other apart because each magnet has two poles. Bipolar disorder, two opposite moods. The person is either too happy or too sad. A polar covalent bond, which means that the bond is different on the two sides of the bond. And why would that be? It would be because the electrons are shared unequally by the atoms in the bond. And the classic example of a polar covalent bond is water molecules. So that's what this is. One oxygen atom and two hydrogens. This oxygen has 6 electrons in that shell. It would like to have 8. So if it would share 1 electron with this hydrogen and 1 electron with this hydrogen, it would be like the hydrogen's gaining an electron, the oxygen is gaining 2 electrons. So like this. But these electrons that are spinning around the hydrogen and the oxygen, they're spending more time spinning around the oxygen than around either of these hydrogens. And therefore, the oxygen end of this molecule, and these hydrogens are shown like off at an angle, like they're both on the same side of the oxygen. That's how that molecule of water is shaped. But the electron is spending more time over here than over here. So this oxygen end of the molecule, we say it has a partial negative charge. That's what this weird symbol means. That's a lowercase Greek letter delta with a minus sign. That means, in chemistry, that means this end of the molecule is partially negative, just because the electrons spend so much time over here. The hydrogen end is partially positive because these electrons are spending less time here than over here. So that's what we call, these are polar covalent bonds, and this is a polar molecule. Why would the electrons spend more time spinning around the oxygen than the hydrogens? Because opposites attract, again. The negative electrons are attracted to the positive protons in the nucleus. This one has how many protons in its nucleus? The same as the number of electrons, so 8. So this one has 8 positive protons in its nucleus. This one has only one positive proton, one positive proton. So as the electrons are spinning around all three of these, they're going to spend more time around the oxygen just because this has a bigger, more positive nucleus than the hydrogens have. Right? Why? So why do we care about polar molecules? Why is that important? It actually is important because water is very important to living organisms like us. Your body is mostly water. Most of the chemical reactions going on in your body are going on in water. So water has some unusual properties because the molecules are polar. So these are all water molecules, and just imagine this is liquid water here. And all of these molecules are polar, so the hydrogen end is a little positive, the oxygen end is a little bit negative. And so these dashed lines here, dotted lines, show that the positive hydrogen end of this water molecule attracts to the negative oxygen end of this one. Likewise, the negative end of this one attracts to the positive end of this one, and so on. And these weak attractions between separate water molecules are called hydrogen bonds. And I wish we didn't use the word bond for this, because I think of bonds as what holds atoms together in a molecule. Like these are bonds holding the hydrogen and oxygen together. But this hydrogen bonds, these are just weak attractions between separate molecules. They're not holding atoms together within a molecule. But but these are very important in water to give water some of its unusual characteristics compared to other substances. And we'll take a break in a minute, but just consider this. You already know about this. You've probably did this when you were a kid. If you have a container and you fill it with water, you fill it all the way to the rim, you can still add a little bit more, right? And it'll actually pile up above the rim, right? Even though gravity is trying to make it spill over, it's like there's a skin on top of the water preventing it. If you keep adding more, eventually it'll spill over, but why is that? What is that? You know this term, surface tension? That's what that is. It's like a skin on the surface of the water. What causes that is this. All these molecules in the liquid water, they're all weakly attracted to each other, and including at the surface here. So they're all these water molecules are kind of pulling together and forming like a skin on top. That's why you've seen insects can walk on water, some spiders can walk on water. You can even float a needle on the surface of water if you do it real carefully. That's because of these hydrogen bonds, because water molecules are polar. Non-polar stuff, an example of non-polar substance is oil, gasoline, kerosene. Those are all non-polar. So there's no hydrogen bonds between molecules of gasoline or oil, any kind of oil. In fact, if you try to do this with gasoline, you fill it to the rim, you put one more drop, it'll spill over. No surface tension. Insects cannot walk on the surface of gasoline. What happens if you try to mix water and gasoline or water and oil together? You stir it and shake it, and what happens? Does it work? even if you, no matter how much you stir it and agitate it, might look like it's kind of mixed together, but if you set it, let it sit for a minute, what's going to happen? It'll separate. And, usually the water will go to the bottom, the oil to the top, just because water is more dense, heavier. And why that is because if you try to mix the oil and try to mix oil molecules in with these water molecules, there's hydrogen bonds between all the water molecules, pulling them all together. And the oil molecules, no hydrogen bonds. They're not attracted to the water molecules or to other oil molecules. So the oil molecules just get squeezed out of the way. So all the water molecules come together, sink to the bottom, the oil floats to the top. But can you mix gasoline and oil together? Does that work? So can you mix two nonpolar things like gasoline and oil together? Yeah, they mix together just fine. In fact, there are some kinds of gasoline engines that you're supposed to add some oil to the gasoline in the tank. They're called two-stroke engines, like outboard outboard boat motors are like that. So you can mix nonpolar stuff and nonpolar stuff together. Sugar is a polar molecule. Yeah, polar molecule. Does sugar dissolve in water? Yeah. So polar stuff dissolves in polar. Nonpolar dissolves in nonpolar, but they don't mix with each other. Okay, let's take a break. I wanted to talk a little bit more about chemistry. We're not going to finish that chapter, but wanted to talk about this next little bit of stuff about solutions and acids and bases. Oh, Well, okay, well, some terms that we need to know: solution and solvent and solute. A solution is just something dissolved in a liquid, and the liquid is called a solvent, and the stuff dissolved in it is called a solute. So salt water is a solution, sugar water. There can be certainly more than one solute dissolved in a solvent. In living organisms, the solvent is usually water. These terms hydrophilic and hydrophobic. Hydrophilic means water loving. That means something that likes to dissolve in water. So that would be anything that's polar, would be hydrophilic. And hydrophobic means water fearing, so stuff that does not like to dissolve in water. So that would be nonpolar stuff like oils. Okay, water. We talked about ionic bonds, like the ones holding sodium and chlorine together in salt. They come apart in water, and so those ions, the sodium and chlorine ions, they dissolve in water just fine, because a negative ion is attracted to the positive ends of the water molecules. The positive ion is attracted to the negative ends of the water molecules, so those ions dissolve in water just fine. Okay, chemical reaction just means, again, a molecule breaking apart or a molecule being formed. So two atoms come together and make a molecule, two smaller molecules to come together and make a bigger molecule. Metabolism is all the chemical reactions going on in a living organism, like in your body. And there's a lot of chemical reactions going on all the time. Right now, you've got molecules being broken down in your digestive system. The food you've eaten is being broken down into smaller and smaller molecules until they're small enough that they can be absorbed into your blood, and then your blood delivers them to the cells of your body that use those nutrients. And in the cells of your body, there's always new molecules being made. Your cells are always making, especially protein molecules. We'll learn about that next week. about what exactly what proteins are, but proteins do most of the work in cells. Um, um, this law of conservation of matter. Matter cannot be created or destroyed. So in a chemical reaction like these, chemical reactions are written like this. So you've got on the left side, this is what we call the reagents or the reactants. Either word is okay. So this is before the reaction. The arrow represents the chemical reaction, and then this is called the products. This is what we have after the chemical reaction. So CH4, that's a methane. That's what natural gas is, and it burns. So again, a chemical burning is just a chemical reaction with oxygen. So when methane burns, the products are carbon dioxide and water vapor. So that's a chemical reaction. Again, we saw this one already. Sodium and chlorine come together to make sodium chloride. This one is photosynthesis, carbon dioxide from the air, water from the soil. In a plant, we'll use the energy and light to put these two smaller molecules together to make this bigger molecule. This is glucose. And oxygen is a byproduct. So plants give off oxygen as they do this photosynthesis. But in a chemical reaction, there will always be the same elements on the right side as on the left side. So these reactants or reagents have carbon, hydrogen, and oxygen. The products also have carbon, hydrogen, and oxygen. They've just been rearranged into different combinations. Sodium and chlorine on the left, sodium and chlorine on the right. Carbon, oxygen, hydrogen on the left, carbon, hydrogen, oxygen on the right. There would never be elements on the right side that were not on the left side. So chemical reactions do not convert one element into another. They're just combining atoms together, or separating them, or rearranging them into different combinations. Types of energy. I didn't mean to talk about all this stuff right now. I thought there was stuff about acids and bases. Yeah. Okay. I hate to keep skipping around, but I'm going to skip around again. I'm going to skip ahead and talk about this stuff, and then we'll do some lab stuff. So, liquid water is made up of water molecules. So two hydrogens, one oxygen. So these are water molecules. In a liquid or a gas, like the air surrounding us, the atoms and molecules they're always moving, bouncing off of each other, and that movement is heat energy. So the more heat energy there is in something, the faster the molecules are moving and bouncing off of each other. And so in liquid water, that's what's happening. These molecules are always bouncing off of each other. And once in a while, two water molecules, when they hit together, one of them will break apart. And when a water molecule comes apart, it forms these two ions. This is H+, so hydrogen positive ion, and this one's called hydroxide, OH-. And later on, these two might come back together, or this OH- might come back together with this H+ and form a water molecule again. But this happens all the time in water, so at any given moment, in a container of water like this, some of the water molecules will be broken apart into these ions. But at any given moment, the number of H+ in that liquid water would be the same as the number of OH-, right? Because like if there's 100 water molecules broken apart, then there would be 100 H plus and 100 OH minus, equal numbers of both of those in pure water. But if we add more H plus to that water, now that water becomes, it's not pure water anymore. Now it's in what we call an acidic solution. Acidic as in acid. So if we add acid to that water, then it'll be adding H plus and making that water more acidic. And so examples of acids, hydrochloric acid, HCl, just hydrogen and chlorine. If you put it in water, these are held together by ionic bonds. So remember what happens when you put them in water, they come apart. So we get H plus and Cl minus ions added to that water. So we're adding H plus. That's why this is called an acid, because it adds H plus to a solution, making that solution more acidic. So an acidic solution just means it has more H plus than OH minus. Nitric acid, same thing. Put it in water, it comes apart, adding H plus to that solution, making it more acidic. This word base means the opposite of an acid. It's something that if you add it to a solution, it adds OH minus. So this one, sodium hydroxide, which is lye, put it in water, comes apart, adding OH minus to that solution. Now there's more H minus than H plus, so we call that solution a basic solution. Or the word alkaline really means the same thing as basic, so we could call it an alkaline solution. Magnesium hydroxide, that's milk of magnesia. Again, put it in water, it comes apart, adding OH minus. So it makes the solution more basic, and so we call that solution a base. Right? So acids and bases are opposites. I'm backing up here. So in pure water is not acidic or basic because the number of H plus and OH minus are equal. But if there's more H plus and OH minus, it's acidic. More H minus and H plus is basic. pH. You've all heard of pH. pH is just a measure. It's a number. That's a measure of how acidic or basic a solution is. And the pH ranges from 1 to 14. So there's no such thing as a pH of 20. It's in that range, 1 to 14. Right in the middle of that range is 7, and that's what pure water is. It's neither, so we would say it's pH neutral. It's not acidic or basic. But if the pH is below 7, then that means that the solution is acidic. And this pH, the way pH is calculated, it seems backwards because a low pH means more H plus, and a high pH means less H plus. But this is what you need to remember here. Low pH means high H plus, which means acidic. High pH means low H plus, which means basic. These square brackets like this, in chemistry, that means the concentration of that in the solution. So this means the concentration of H plus in a solution. That means just how many H plus are in a solution. Like how many H plus ions per milliliter of that solution or something. If it's a lot, then it's acidic. If it's If it's a low concentration, then it's basic. So here's some familiar solutions and their pHs. So yeah, it's kind of weird the way this is drawn, but above this diagonal line is acidic. It's no, it's basic, and below is no, let's just look at the numbers. So the lower the number, the more acidic it is. So gastric juice, that's the acid in your stomach, very low pH, about 2. Apple juice, a little less acidic. 3. Tomato juice, cabbage, cow's milk, it's just a little bit acidic. It's 6.6, just a little below 7. And then anything above 7 is basic. So human blood, pH of human blood about 7.4. Sodium bicarbonate, that's baking soda. That's basic. Egg whites, basic. Milk of magnesia, we saw saw a minute ago that's basic. Ammonia, pretty strong base. One thing that bases have in common is if you get them on your fingers, they feel soapy and slimy. So like ammonia, if you get that on your hands, or bleach is a pretty strong base, feels soapy and slimy. Even baking soda and water, it feels like soapy. Acids don't feel that way. Acidic solutions don't feel soapy and slimy. Okay, okay, we'll talk about buffers and then we'll stop. A buffer is just a chemical that, if it's in a solution, it stabilizes the pH. That means if a solution has a good buffer in it, then if you add a little bit of acid to it or a little bit of base to it, the pH will stay the same, because that buffer will soak up the H plus or add more H plus as needed to keep the pH the same. And that's important in anatomy and physiology, because your body has buffers. You have buffers in your body fluids, in your blood. That's why, for example, lemonade, you think that's acidic or basic? It's acidic, right? Lemon juice is it's a pretty strong acid, acidic solution. But if you drink 3 glasses of lemonade, the pH of your body fluids, the pH of your blood is not going to become very acidic all of a sudden. That's because you have good buffers in your blood that will stabilize or keep the pH about the same as it's supposed to be. In fact, this is one of the buffers right here in blood. In your blood, you always have these three things. You have these carbonic acid molecules that, if these come apart, they form an H plus ion and this bicarbonate ion. Like if you would drink a lot of lemonade, then you're adding a lot of H plus to your blood, right? Making it more acidic. But you've got so much of this bicarbonate in your blood all the time that those H plus ions that you're adding will combine with these bicarbonate ions to form these carbonic acid molecules. So it's taking these H plus out of the solution to keep the pH at the normal level. If you would eat if your body fluids, your blood would start to become too basic. You've always got plenty of this in your blood these molecules will come apart and add more H plus to your blood as needed to keep the pH where it needs to be. That's why there's this reaction arrow has the arrowhead going both ways, because this will just go either way as needed to add more H plus to your blood or take H plus out of your blood to keep your pH where it's supposed to be. So it's a very good buffer system. So let's stop here. And, still need to take attendance, I guess, unless I can count and everybody's here, but I don't think so. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, 2 people missing. So I think after tonight, I'll just pass around the sheet and you can just initial it if you're here, so I don't have to take attendance like this. Graceland, Twinkle, Mary, LaTracy, Kelly, Melissa, sure, Hannah, Kahela, no Kahela, Tiana, no, Shania, I'm sorry, Shania, yeah, I knew that. Sherry, Ashley, Crystal, Sharonda, Shaquala, Kaylin, and Keisha, okay. Is that everybody? Did I call everybody? Anybody I didn't? Okay. Well, let's look at this handout for a minute. Maybe we can make out here a little early tonight. You guys can. I have to see the late session. Okay. Most of this is pretty straightforward. Name the body cavities, name planes, directional terms. Name one organ from each of the following organ systems. That's pretty easy, right? Do that. Name one organ within or surrounded by each body cavity. We'll be able to do that. Body cavity where each organ is located. That should be easy. Okay, what's the opposite of each of these directional terms? That's the medial is lateral, distal is what? Proximal, superior, inferior, superficial, deep, and anterior, posterior. Okay, using the most appropriate anatomical terminology, complete each statement. Patient has broken his right leg 5 centimeters above his knee. This could be described as a fracture of the femur bone 5 centimeters. What? Proximal. Proximal means closer to the torso. The ears are located. Did we learn the word contralateral? Let's say contralateral. Yeah, contralateral means on opposite sides. Um, uh, the palate or the Richmond mouth is located what to the tongue? Above,
I mean, superior.
superior. Um, the nose is, I guess, anterior, anterior to the brain. The skin is superficial, at the surface, or the surface. Right? The right lumbar region is what to the umbilical? Lateral, means off to the side or farther away from the center line. Okay, patient has a stab wound 7 centimeters above his belly button. So that could be described as 7 centimeters what to the navel. So above would be superior, right? The abdominal pelvic cavity is what to the pericardial cavity? Inferior, right? Because pericardial is here, and abdominal pelvic is down here. Hypogastric, which is down here, right, is flanked to the epigastric, which is here. Would be inferior, right? Patient complaining of pain and tenderness in the right hypochondriac region, which would be up here, right? Which quadrant would be that? Right up here. Okay, I think we may have looked at some of these last time. Which section view would expose the heart, both lungs, and the spine? Yeah, I'll transverse. None of the others would do that. Right? The brain on both shoulders. Frontal this way would do it. Transverse wouldn't do it, and mid-sagittal would be in between the shoulders. Both ears, but not the nose. Frontal this way. Frontal. The nose, but neither ear. Yeah, so a mid-sagittal this way would do it. This is a frontal if it was far forward, cutting off the nose. The ears would be behind that. Both ears, the nose, and the brain. Both ears, the nose, and the brain. So transverse would do that. Okay. And fill in the blanks in this paragraph. From that word bank. In the anatomical position, the face and palms are on the what body surface? The anterior? So facing forward, right? Anterior. The buttocks and shoulder blades are on the posterior. Yeah.
It could also be home or well, no, not position if you stand.
The top of the head is the most light part of the body. Superior. Right? The ears are blank and blank to the shoulders. Lateral.
Medium.
They're medial, right?
Yeah.
And superior.
Yeah.
I guess that's it. And blank to the nose. Posterior. The ears are posterior to the nose. The heart is blank to the vertebral column. It just Anterior, in front of, right? Anterior. And blank to the lungs. The heart is blank to the lungs. Medial, right? In between, so closer to the center line. The elbow is blank to the fingers. Proximal, but blank to the shoulder. Distal, right? Distal. The abdominal pelvic cavity is blank to the thoracic cavity. The inferior, and blank to the spinal cavity. Anterior, right in front of it. In humans, the dorsal surface can also be called I didn't use that word. I kind of avoided that word dorsal because we don't really use that very much in human anatomy. But that's also the can also be called the
Central.
Posterior?
Yes.
Yeah, I think so. Posterior. Yeah. However, in quadruped animals, the dorsal surface is the top, above, the superior. Yeah. Quadruped animals mean animals with four legs. If an incision cuts the heart into right and left parts, the section is a sagittal or mid-sagittal. But if the heart is cut so that superior and inferior portions result, that would be transverse, but implicit. You are told to cut a dissection animal along two planes so that the kidneys are observable in both sections. The two sections that meet this requirement are the transverse would do it, and what else could do it? Frontal section. Okay, anything else? Crossword puzzle, anybody get that? I don't have an answer key for that. I found it on the internet. Well, let's, I don't know, what can we do for lab activity for this stuff? I don't know. These, that number 4 on the ceiling, and there's a few years ago, several years ago, we stuck numbers. We put like the number 1 there, and it's number 4, and I don't know, there's some more, there's a number 3 there. And we had a worksheet, some of us anatomy instructors had a worksheet that used some of these things, and it was like, what position would you be in, or the stronger position if you were looking at that number? What position would you be in if you were looking straight at that number? Like if you were lying you'd be lying face up on that table. It's called supine, right? And I don't know. I forget what position could you be in where you'd be standing at that number? If you were like prone on it, lying on here, I guess. But, I don't know what else. Then we used to, some of the instructors we had modeling clay, like Play-Doh in one of the stores back there. And we used to have you make little figures out of little people how to play, and then use string to actually make digital cups and transverse cups or whatever. We don't need to do that. It's kind of childish. I was this thing over here. Can I tell you what that is? It's called an atomage, like an atomy image maker. And it's really cool. I haven't learned anything about how to use it yet, but the nursing department bought that for us. I think it costs like $80,000. And but it's this is all of you take this cover off, and this is just a big glass screen here, and it's a touch screen, and there's 5 different cadavers, cadaver images, and the actual cadaver, the images made from the cadavers of 5 people, named Bill and Mary, and you can pick them, and some like there's some of them had diseases. I was looking at one today. The lady died of stomach and intestinal cancer, and you could see the cancerous tissue in the image. It's and you can see the person's whole body, and then you can take these section views at any level, in any direction, and see inside. And you can select, well, you could just select, like I could say, I just want to see the skeletal system, and then everything but the bones will disappear. Or just the circulatory system, everything except blood vessels will disappear. Or just one organ. So say I just want to see this small intestine, everything else will disappear. And you can rotate it. And so it's amazing. I need to learn how to use it, so that is something that this is me. I'll forget this right as I'm retiring. So. Okay, well, let's do this little chemistry. Just a few minutes of chemistry, and then we can leave early. You guys can leave early if you want to. So everybody just come over here for a minute. This is from another class. I don't know. This is all. Distilled water. What's this thing called? Do you know what that's called? It's a beaker. Chemistry is called a beaker. Why is it called that? We're using a beaker. I'm going to put some distilled water. So we learned about pH, which is a measure of how acidic or basic a solution is. This is just pure water distilled. So what should its pH be? We use a pH 7, right? No. Below 7 is acidic, above 7 is basic, right at 7 is pure water. And one simple way of measuring pH is this stuff, is the pH paper or litmus paper. And it's colored. Got a color coding chart on there, so you just put it in the solution, and it'll change color according to pH, and then you compare it to the little chart there. So you can just pull out the piece and carry along. So somebody want to test the pH of the water? Just volunteer. No,
Stick it in.
just tear it off. Just stick it in for a couple seconds and just pull it out. Yeah, what is it? closer to 6. There's no 7,
Right.
but
So it's close to 6.
yeah, if there was if there was a 7, it would probably match. But it's just 2, 4, 6, 8, 10. So it's about what it should be. Um, um, but what about yeah? Do you want to do this one? This is small that.
Oh, let's read it.
Good. So it's acidic, right? What, did you recognize the smell? Vinegar. It's white vinegar, which is acetic acid, 5% acetic acid in water. You can just put that on the piece of paper down. Okay, so we expect that. Uh, that's the result we expected. How about this powder is baking soda? Let's put some of that water in there. Somebody want to volunteer to test that? And what do we think that's going to be? Acidic or basic? Baking soda. It's basic. Match up with them there. So it's above 7, right? So it's basic. Um, baking soda is a base. When I was a kid, my dad used to mix baking soda with water and drink it when he had an upset stomach. And the idea is that his upset stomach was from stomach acid. The base would neutralize some of the acid. So when you mix an acid and a base together, you get a pH somewhere in between. So you say it neutralizes each other. Okay, what about this? Lemon juice. Let's try that. Mm. What's the problem with using these? What's the limitation? Like, what kind of solution could you not use these on? Would that, if we were testing the pH of grape juice, you think that would work? Because the grape juice has a strong color itself, that would change the color of it. So I'm gonna put a little water in, just because that lemon juice has some color. Okay, so we want to do that one? Just stir up a couple inches. Just keep it in there for a couple seconds. Okay, so that means, okay, so it's quite acidic. If you got an acid in a cut or something, it burns, right? But what about bases? You've got a strong base on your skin. Would that hurt you? Something like lye. Lye is a very strong base. And it can burn you just as bad as acid. Either one, if there's a strong base and acid. The strong base, the term for that is described as caustic. Like, oven cleaner is a very strong base. Like caustic. Okay, one more thing I thought would be kind of cool to do. Um, so, um, 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 Your cells are always producing carbon dioxide, and that goes into your blood, and then in your lungs, you exhale the carbon dioxide to get rid of it. But so it's a waste product. But we need to have some carbon dioxide in our blood because that helps to maintain the pH of our blood. In fact, if a patient or somebody hyperventilates, he's breathing, usually if they're in an anxiety attack or something, they can't stop breathing too fast, you can exhale too much carbon dioxide and it'll cause the pH of your blood to become too basic because carbon dioxide dissolved in water forms with carbonic acid. So you need to have the right amount of carbon dioxide in your blood, not too much, not too little. Anyway, put some water in here, some more distilled water, and this stuff is called phenol red, and this stuff is sensitive to pH. It's red color. I don't even have to measure this. So that's red, right? But if it becomes more acidic, it'll turn from red to orange and then yellow. So if somebody would blow into that, let's put a soda straw in there and blow into it. So we're adding carbon dioxide from the breath into this solution. And as that carbon dioxide dissolves in the water, it'll become more acidic. Okay? And it should change color from red to orange and then yellow. So should we try that? See who wants to blow? We need a volunteer. Somebody. So I'm going to put this light behind us to make it easier for the rest of us to see if it changes color. So just have a clear thing for me. So put it in there, and let's put this over there so you don't splash it on yourself. It's not toxic or anything, it won't hurt you. But this is burning orange and yellow. And yellow. Is it working? Okay, yeah, I can tell that. So you're alive. Exhaling carbon dioxide. Okay, I don't know. Just want to get out of here.
Can you turn on Beck? Can I see that?
I don't know how to turn it on.
Oh.
I was looking at it when one of the other instructors had it going. Maybe my next week I'll figure out how to do it.
No, actually, wait, are you coming early? Yeah. What time? I'm sorry, sir. Yeah. So you wanna get here? Next week I got a meeting. Oh, wait a minute. Next week I got a meeting. I'm sorry. Oh, okay. So you can't come in? Yeah, I'm coming next week, so I want to do it out Thursday.
So me, you, me, what?
You just hear me, how come we're here? The room be open. It's gonna be open. Yeah, I don't get on here.
On my city room, 85, and I'll be at 5.
Yeah, and I get here soon as I can. I just got to meet next week.
Okay,
I'll just come on, every week I'll just come on.
okay. All right, that works. And then we can kind of go over
What we been.
what we've been doing here. Okay. Hey, Mr. Beck, I have a question. I took the, chapter 1, short answer, and I didn't get any right, and I know that's not right, like, there's no way I did not get any.
Oh, but that's just because, yeah, I should have said something about that. Those short answer questions, if your answer is not exactly the same as an answer stored in your like letter, it'll say it's wrong. Or even if you put an S on the end of the word and make it plural, it'll say no. So your answer is probably fine. But, after the deadline, I checked all the answers that Moodle said was wrong.
Okay.
Oh,
And if they're right, I change the grade.
All right, thank you. Hey, girl, did you park in the right spot?
I did, and did. Did you? Yeah.